All right, dot plot shows the height in inches of 25 students in my stats class. The mean height is 67 and the standard deviation is 4.3. And you can get that information right here. The question asks, find the percentile for Lynette, a student who is 65 inches tall. And then the hint that I gave you is count the number of dots that are equal to or less than 65. So here's our 65. So we're going to count all the dots to the left of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the percentile is going to equal the number of dots, that was 10, out of the total number of dots, which was 25, and 10 divided by 25 is 40%. All right, classmate of Lynette's is Morty, and he's 71 inches tall, in the 84th percentile. This means that, all right, so anytime you're dealing with a percentile, it represents the percent of the population that is less than or equal to the given percentile. So this tells us that 84% of his classmates are equal to or less than his height. All right, so that means he is taller than or equal to 84% of his classmates. All right, so when I measured these heights, I made a mistake and I found out that I had to adjust each dot up here by 2 inches. So each one of these dots is going to end up moving 2 inches to the left. All right, what would be the new mean and what would be the new standard deviation? Okay, when you adjust by adding or subtracting, in this case I'm subtracting 2, okay, it changes the mean, the standard deviation does not change. All right, so when we look up here, our mean is 67, so the new mean is going to be the old mean minus 2 inches. So the new mean is 65 inches. Okay, now everything is moving 2 to the left, so the spread doesn't change. And that's our standard deviation. That's the spread. So it stays 4.3 inches. So our new mean is 65 and the standard deviation stays 4.3. Okay, suppose I want to take all these heights and change them from inches and into centimeters. So to do that, I'd have to multiply each number up there, each dot, by 2.5, its value. Right? When you multiply all the data by, or divide, it changes the mean and the standard deviation. So to get the new mean, I'm going to take 67 and multiply it by 2.54, and I get 170.18. Okay, and then to take the standard deviation, I'd also multiply it by 2.54, and I get 1092. So my new mean and standard deviation is 170.18 and 10.92. Both of them change when you're multiplying and dividing. All right, number 5. We've got 2 skewed graphs, and the question's asking you to find the which one of those lines up there is the mean and which one's the median. So here we've got a skew to the right, that's the direction of the tail, and number 2 is skewed left. All right, now the mean is the most sensitive out of these two things. It's going to move more than the median is. So the mean is always going to be the line that is closest to the tail. So in this case, the mean would have to be C. And in this one, the one closest to the tail is going to be A. All right, the next line over then is automatically going to be our median. Okay, so the median got moved, but it doesn't move as far as the mean did. So in this case, our median is B, and in this one, our median is also B. Okay, the A in this one, would be the mode, which we're not dealing with, and the C in this one would be the mode. All right, so our answer is our first option. Okay, an internet reaction time test asks subjects to click their mouse button as soon as a light flashes on the screen. The light is programmed to go on at randomly selected time between 2 and 5 seconds after the subject clicks start. The uniform density curve below models the amount of time the subject has to wait for the light to flash. Find the height of the uniform distribution. And it tells you the height of a uniform distribution looks like a rectangle here, is equal to 1 over the length of the rectangle. All right, so this rectangle, its length would be 5 take away 2, which is 3. So my height is 1 over 3. Okay, number 7, we're using the same distribution, and it's asking what proportion of time will the light turn on between 2.5 and 4 seconds after the subject clicks start. So our first step is shade the portion of the uniform distribution between these two values. All right, so I'm just going to estimate, I'm going to say 2.5 is about there. So I'm going to draw a vertical line, and then 4, I don't know, maybe about there. And now this rectangle I'm going to shade, and I want to find its area. All right, well, that rectangle that I just shaded has a height of 1/3, and it has a base of 4 take away 2.5, which is 1.5. So to find my area, I'm going to do 1/3 times 1.5. And that would give me 0.50, which is equal to 50%. The density curve shown models the distribution of a quantitative variable that is equally likely to take any value from 0 to 2. All right. What percent of the observations lie between 0.5 and 1.2? All right. Now, these answer choices, just ignore this over here, guys. Okay, it says shade the portion of the distribution between 0.5 and 1.2, and these aren't seconds, these are just number values. So 0.5 would be about there, 0.5, and I'm going to say 1.2, maybe about there. So I'm going to draw a rectangle, shade that in, and find its area. Okay, so that skinny rectangle, its height is 0.5, and its width is 1.2 take away 0.5, which is 0.7. So to find the area of this, I'm going to multiply those two numbers, 0.5 times 0.7, and that's equal to 0.35 or 35%. Okay, question 9. All right, student scores were normally distributed with a mean of 68 and a standard deviation of 11. So you add 11, subtract 11, and you're going to get these other values here. Okay, now the question's asking what percent of scores are between 57 and 79, and your hint is use the empirical rule, which is right here. Okay, so 57 to 79 would be this portion. As you can see, this is one standard deviation above, one standard deviation below, and between those two standard deviations, that's right here, that would be a total of 68%. Okay, student test scores, so it's the same distribution. So when you see this notation, remember, that's telling you that's the mean 68, and this is your standard deviation. Okay, what percent of scores would run between 35, that's -1, -2, that's -3 standard deviations. Okay, that's right here. All the way up to 79, which is 1 standard deviation. So I am finding this area. Okay, so I'm going to take these values, there's -3 standard deviations up to 1. So these values I'm going to take and add those up. Okay, so these two are 68. And I'm going to add these two, and that's going to be 15.85. And then I'm going to add those two up. So that would end up being approximately 84% when I added up those values. So we're back to our same tests distribution, and this one is saying what percent of the scores are below 46. All right, so here's 46. Okay, that's 2 standard deviations below the mean. Okay, so our 2 standard deviations below the mean is right here. So I'm going to take all of these two values and add those up, and that's going to be my total. So 0.15 and 2.35 adds up to 2.5%. Okay, student test scores were normally distributed, so same thing. What test score corresponds, looks like I misspelled corresponds there, to a z-score plus 2. So each one of these is one z-score. So this would be a +1, this would be a +2. So that would match up with 90. That would be 2 standard deviations above. Okay, use the z-score table to find the proportion under a curve that is to the left of -1.08 as a z-score. All right, so when we're talking about a z-score, that means this normal curve has a mean of 0 and its standard deviation is 1. So this would be -1, -2. This would be a standard deviation of 1, 2, etc. So the question is, well, what would the proportion be if I went to -1.08? So that would be just a little bit past -1. So maybe somewhere about there. And I want this area of the curve. All right, so to get that, we're going to go to our Z table, and we're going to find that the area is going to be at the intersection of the row that starts with -1, all right, and then it goes to the column 0, 8. So that gives us our Z-score of 1.08. So I want to be sure I'm on the negative table, which is right here. And I'm going to go to the row that is -1, 0, which is right here. And then I'm going to go to the column that is 0, 8, which is right here. And I'm going to find the intersection of those two. 0.1401, and I'm going to change that into a percent by moving the decimal 2 places over. So that area is 14.01%. Okay, now it says using the Z-score table, find the proportion under a normal curve that is to the right of the Z-score -1.08. Okay, so if I go to that location again, this would be -1. So we're talking, maybe about there. I'm going to shade that in. But I don't want that area. I actually want the area that is to the right of that. Okay, so the area that I'm going to get is this area. So to do that, I go to my table, and the table is going to tell me this area right here. Then I'm going to take that and subtract it from 1. So I'm going to do everything like I did the last problem, but since we want the proportion to the right, I'm going to subtract the area number that I get from 1. Okay, so whatever I get for this part here, I'm going to subtract it from 1. Okay, so we already know what that value is from the previous problem, 0.1401. And then I'm going to take that from 1 to get this area. So this area is going to equal 1 subtract 0.1401. Okay, so this was the area that we got in the previous one. That was to the left. So to get the area to the right, I'm going to take that and subtract it from 1. And that leaves me with 0.8599, which is 85.99%. That's the area of the right of that Z-score. All right, find the indicated Z-score for this area. So that area, 83%, that's the same as 0.8300. So I'm going to go to since this is more than 50%, I'm going to go to my positive Z table, and I'm going to find the value in the body that is closest to 0.8300, which looks to be about, let's see, this is 8389. That would be 11 away. And then you got 8315, and that would be 15 away. So the 8289 is closer. So then the Z-score that goes with that would be 0.95. All right, so then I take that, that's my z-score. This would be 0.95. All right, find the indicated z-score for the shaded area. So you're told that this red or this white portion here is 20%, which means this has to be 80%. So this is its table value, 0.8000. So I'm going to go over to the body of my table now and find that number. Find the closest number to 0.888 in the body of the table. Okay, so this is the body of the table here. So 0.800. All right, so here's 0.823, 0.7995. That would be the closest. So to get the z-score, I go out to the margin. Okay, that's the first part of my z-score, 0.8. And now I'm going to go up to the margin, and that's the second part, so that's going to be 0.84. That is the z-score that goes with this area. That's the closest we could get to 0.800. All right. The distribution of scores in the math section of the 2019 SAT test were approximately normal with a mean of 528. So you'll have to be able to draw this. I gave you the drawing, but you're going to have to be able to draw this on your own. So my normal curve here, what this tells me is right in the middle is 528. So I'm going to draw a picture that looks like this. The standard deviation is 117. And then the question is, what proportion of the students scored less than 350? Okay, so I'm going to kind of estimate, 350, I don't know, maybe about there. I'm going to draw a line. That's my 350. And the question's asking is, what is this proportion? What proportion right here of this normal distribution is shaded? Okay, so that's our first step right there. That's done. Okay, the second step is convert 350 to a z-score using this equation. All right, so to take 350 and turn it into a z-score, okay, my formula is the z-score is equal to whatever my value is. In this case, it's 350. Take away the mean, and then I'm going to divide that by the standard deviation. So I end up getting a z-score of negative 1.52. All right, now I'm going to take that and go over to my table. I want to get the negative z-score table, and I want to find the number that's in the body of the table, and that's going to give me my proportion. Right? So now we'll go over to negative 1.52. So I'm going to go to negative 1.5 right there, and then I'm going to go over to 0.2. And where these two intersect, that's my area. So they intersect at 0.0643. So that's this area right here, 0.643, which is about 6.43%. All right. Ball speeds professional tennis players serve can be modeled by a normal distribution with a mean of 112. And again, you're going to have to be able to draw these normal distribution graphs. You won't get a picture like this. So this is 112, normal distribution 112, standard deviation 5. And the question is asking what percent of the serves are greater than 120. So 120 would be over here to the right, and it's asking for the area to the right of that. So when we are finding the area to the right, we got to remember what we get out of the table, we have to subtract it from 1 to get the area to the right. All right, so our first step is we drew and we labeled, shaded. Okay, next convert 120 to a z-score. So z is the score, 120, in this case, the speed, minus the mean, which is 112, divided by the standard deviation 5, and I already did that over here, and I got a z-score of 1.6. Now I'm going to go over to my table and I'm going to get the proportion, but then I've got to remember I'm going to subtract that from 1 to get the area to the right. All right, so 1.6, I'm going to go to 1.0, and then I'm going to go over to the column 0, 6. 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6. Okay. So my proportion is 0.8554. Okay, 0.8554, and then I'm going to subtract that, and you can see I get 0.1446, which is about 14.46%. That's the shaded area right here. Okay, now we're doing the reverse of what we did in the last two. Now we know the proportion and we want to figure out what's the value right there. Okay, so we're back to our SAT information here. So we always draw and label. So I gave you the drawing, but you'll have to provide it on the test. Okay, and you're told this is 528. It's a normal curve, 528, and the standard deviation 117. Okay, and the question's asking, find the math score located at the 39th percentile. Well, 39th percentile, that's 0.3900. Now, where you draw that is, you know that this is the 50th percentile, right where the mean is. So 0.39 is going to be somewhere to the left of that. You know, I don't know, maybe about there. Okay, and that's why I'm labeling that 0.3900. So now you're going to go over to your Z table and find in the body the closest value to 0.3990, and then you're going to get the Z-score from the margin. All right, so this is to the left of the mean. Okay, so I know. All right, so the closest to 3900 are these two, 0.3900. And the one that's closest, this one right here, this is 0.026 away from that, and this one is 0.0013. So the 4013 is closer for out of. All right, so the z-score that's associated with that is going to be negative 0.2. That's from this row, and then I go up to this column, that's 0.5. So that's my z-score for that particular situation. All right. Okay, so that takes care of our second step here. Now our third step is we're going to use the z-score formula to get this missing value here. All right, our z-score formula says this. The z-score is equal to the value that we're looking for, or in this case, the score, minus the mean divided by the standard deviation. Okay, so I know three of these numbers. I know the z-score, so I can take that out and replace it with negative 0.25. I don't know the score. That's what I'm trying to find, so that's x. Okay, the mean is 528, and the standard deviation is 117. Now what I'm going to do is solve this equation for x. So to solve that equation, I'm going to multiply both sides by 117. And over here on the right, these are going to cancel, so I'm going to be left with x minus 528, and then I get negative 2925. And now I'm going to add 528 to both sides. Those cancel. And I have my score. And now I'm going to add 528 to that score. 528. And I end up getting 498.75. And that is my SAT score. Okay, number 20. The ball speed for professional tennis player serves can be modeled by normal distribution with a mean of 112 and a standard deviation of 5. So when you draw and label here, okay, here's my drawing. And the question is, what's the ball speed at the 85th percentile? Well, that is a percent, so this is your 85th percentile right here, which means this area off to the left of it is 85%. Okay, so what we're going to do now is we're going to find what's the z-score that belongs to that, and then use the formula to get what this score is right here. All right, so we're going to go over to our positive z-table and find the z-score that is closest to 0.8500. All right, so our closest value to 8500 would be 8508. So when I go over here, that's going to give me my z-score. And that's going to be 1.04. Z is 1.04. Okay, so now we go back. So for our second part here, we've got a z-score of 1.04. Now we're going to substitute that into our z-score formula and figure out what this missing score is right there. Okay, so we know that the z-score is equal to, in this case, the speed that we're looking for minus the mean divided by the standard deviation. Okay, and our z-score is 1.04. So we're going to solve this equation for x. So we do that by multiplying both sides by 5. All right, so 5 times 1.04 is 5.2. Then I'm going to add 112 to both sides. And I end up with 117.2 is equal to x. So that's 117 miles per hour. That would be this number right here.